Okay, so this is problem number 1 on our power worksheet. We're going to just start listing our variables, and then we'll determine what equation we can use based on those variables given. Okay? So the first thing it says is that it starts from rest. What variable does that give us?
Velocity.
Yeah, velocity initial. Velocity initial is equal to 0. Our velocity final then would be equal to 27. Good. And we know that our time is 2.8 because that's given to us in the problem. Okay. There's something else that we know? Good. Mass. Do we need to convert it? No, because it's already in kilograms, which is what we want. All right. Our overall goal here is to find average power, which is P equals work over time. Are we given work? No. We're given time. We want to find power. So which of those work equations could we use here to solve for? All right, so we have, we have mass, we have velocity, we have time. So we need to use our change in kinetic energy, change in kinetic energy to solve for work to go into this problem, okay? So we can say power equals delta KE over time. All right, remember delta or change in means final minus initial. So we'll take kinetic energy final minus kinetic energy initial. Okay, that's what the delta means. You guys know that? So we'll go ahead and start plugging in some numbers down here at the bottom. Kinetic energy final, the equation for kinetic energy is what?
1/2 mv.
Good, 1/2 mv squared. This is our final here. 1/2 times mass times velocity squared. Yeah, we're doing that right now. So this is our final kinetic energy right here. And our initial kinetic energy, what would our initial kinetic energy be? 0, because we start with 0 velocity. So if we plug in a 0 velocity to 1/2 mv squared, we're going to get 0 for our initial kinetic energy. Okay, does that make sense? Okay. This term right here would be kinetic energy final. This term would be kinetic energy initial. Okay, and we're going to take all that over t, which is 2.8 seconds, which means our power comes out equal to what value in watts? Matt, what'd you get?
650,000.
650,000 what?
892.85.
Perfect. Okay, that's in watts. Do we remember how to convert from watts to horsepower?
Divide by 746.
Good. Divide by 746. So we'll take that divide by 746, and we'll get that value in horsepower. All right, what do we get for our horsepower value?
872.5.
872.5. Do we agree?
Yep.
And our units for horsepower are just HP. So number 2 on the power worksheet says a weightlifter raises a barbell with a mass of 100 kilograms from the floor over his head in 2 seconds. What's his average power input? So how much power is he having to use? We want both watts and horsepower here. All right, so first of all, they give us our mass. They give us a height. And they give us a time. Okay, our overall goal here is to solve for power. What version or what equation for work should we be using here? Yeah, we'll use our potential energy. So work is equal to change in potential energy. All right, so As he starts to lift this mass, before he begins to lift it, what's his initial potential energy? 0. His initial potential energy is 0 because he's starting on the ground. It's at no height above the ground at all, which means it has no potential energy. Okay, so the beginning or the initial potential energy would be 0, which means we can just use power equals mass times gravity times height over T. Okay, whenever our initial is 0, we can just take out the delta, and we know that power is equal to mgh over T. Okay?
Wait, potential energy is over T?
Change in potential energy is work. So this term right here could be equal to potential energy and also equal to work. Okay, because there's no initial potential energy. Oh, wow. Okay, so power equals 100 times 9.8 times 2.5 all over 2. Parker, what'd you get?
1225.
Good. And our units for that?
Watts.
Good, watt. Okay, when it comes right out of our power equation, it should be in watts. We want it in both watts and horsepower, so when we convert it to horsepower, we get
1.64.
746. Divided by 746. All right, let's try number 3. A 60-kilogram hiker climbs a hill 1,200 meters high. If he can generate a power of 500 watts, how long will it take him to climb the hill? Okay, so this one, they give us the power. Uh-huh. Yep, just P. 500 watts, and it's in watts. We don't have to do any conversions. We have a mass of 60, and we have a height of 1,200 meters. Oops. Okay. This instance, he's climbing, he's hiking, he's moving up somewhere. Okay, just like you were running up the stairs and we calculated your power output, we're going to do the same thing for him. Okay, he's traveling a vertical distance, so we'll say P equals mgh over T. Okay, because he's doing that work to overcome gravity. His initial potential energy must be 0 since he starts on the ground at a 0 height. Okay, and he ends up 1,200 meters above where he started. So we'll take 500 watts is equal to mass times gravity times the height all over time. And that's what we're trying to solve for here is T. Yeah, it'll probably be a big number. He's kind of 1,200 meters, so it'll take him a while. What's our shortcut for solving for this T right here? Yep, switch these two places. Okay, about 1,411 seconds. What if I asked you to put that value into minutes?
You would divide by 60.
Yeah. Okay, so if I asked for it in minutes, you'd divide by 60. If I asked for it in hours, you would divide by...
112 today.
No.
If I wanted you to put it in hours, you could say 3,600 seconds in 1 hour. Or you could say 60 seconds in 1 minute, 60 minutes in 1 hour, and you'd divide by 60 twice. Okay, you could do it either way. Okay, but we can just keep it in seconds here. Number 4. A car moving at 27 meters per second or 60 miles per hour encounters an air frictional force of 200 newtons. How much power must the engine generate to maintain this speed? To maintain. Okay, so if we have a force that's due to friction, so if we have a frictional force of 200 newtons, and I want to maintain that speed, if I want to travel at a constant velocity, what's that mean about my net force?
0.
It has to be 0. My net force has to be 0. Okay? So if I want to maintain that speed and I want my net force to be 0, how much force do I have to apply to keep this speed up, to balance the frictional force? 200 newtons. So that means my applied force must just be 200 newtons. The frictional force could be negative, yeah. Frictional force would be negative. Okay, so my applied force here is 200 just because it says we want to maintain that speed. We want to be at a constant velocity. Okay? And then it also tells us that we have our velocity of 27 meters per second. If I want to find power, which equation can I use?
V times F times
Energy transformed.
I can use power equals force times velocity. Okay, because we were given both a force and a velocity, so we'll figure out an equation that those fit into. Okay? Good. All right, let's try number 5. Okay, a 100-watt light bulb has a life of 2,000 hours. How much energy does it consume over its lifetime?
hours to seconds.
We're going to have to put hours to seconds. That's right.
So multiply by 65.
Big number.
2,000 hours. So you can either say, sorry, Margaret, you won't divide, you'll multiply?
Yeah, that's what I said.
Okay. 1 hour is equal to 3,600 seconds.
Yeah.
Okay, which is about 7.2 times 10 to the 6th. You can,
7,200,000.
yep, you can leave it like that, or you can put it in scientific notation. Either way. What is the 100-watt light bulb tell us? What variable does that give us?
The power.
Yeah, power, because it's in watts. So if you're unsure as to what it's, what really variable it's giving us, look at the units that goes with it. Okay, so
Kilowatts per hour. Could you just...
we're gonna do that. We're gonna do that in a second. So I'll show you. Okay. So we want to solve for the energy. What variable then are we gonna be solving for? Kind of. Remember that work is the amount of energy that's transformed.
So it's joule. So work.
Yeah, that's what we're solving for. We're just solving for work. Okay, because work is the amount of energy that's been transformed or the amount of energy that's been used. Okay, so we're going to use P equals work over time because we have P and we have T. Yeah, exactly. Just add 2 decimal places on. Okay, so 7.2 times 10 to the 8th. And what's our unit for work? Joules. Very good. Joules. Okay, so there's our answer in joules. It also says we want our answer in kilowatt hours. Okay, and kilowatt hours is a typical energy unit for houses. Okay, that's kind of how you measure your energy intake and output in houses. Okay, is in kilowatt hours. So if we want our units to just be, can I get rid of some of this? Bless you. If we want our units to just be kilowatts times hours, what's that mean we need to put our power and our time into? Yeah, we need it to be in kilowatts and hours. Rather than converting our time to seconds, we're going to leave it in hours, so we'll take 2,000 hours here for our time. And if our power was in watts, how many of the base of anything is in a kilo? 1,000. Okay, so if there's 1,000 watts in a kilowatt, how do I convert watts to kilowatts? Divide by 1,000. I'm going to move that decimal place 3 places to the left. And that gives me kilowatts. Together. Okay, if I want kilowatt times hours, I'm going to multiply it just like I did down here and solve for work in kilowatt hours. Exactly, so we'll take 0.1 kilowatts equals work over 2,000 hours. And that gives me 200 kilowatt times hour. Okay? Okay, try number 6 on your own. It says a 2-horsepower winch is used to raise up bricks. That's a 30-meter tall building if the bricks need to get to the top in 2 minutes. What's the mass allowed?
It's not how I believe it.
What do I need? Kilograms? Yes.
Can I go see Miss Blank?
It's a god. I have a stone. I let it go by a stone.
I wrote it down wrong.
So the order of doing this doesn't matter, right? So like if I times the 9.8 times 30 and then divided by 120 and got
Yeah, that's fine. Then
and then divide by
yeah, that's fine. You have to take 1492 divided by that answer. You got 609?
yeah.
Yeah. We're going to talk about potential energy of a spring, looking at this kind of demonstration right here. When we're talking about a string that's just basically at rest, we consider it to be in its static position or its equilibrium position. Okay, it's not being stretched, it's not being compressed, it's just sitting there relaxing. Okay, it's in its static position. When we compress it, means we're going to smush it down, okay, make those springs coil even tighter. When we stretch it, we're pulling it out. Okay, so everyone understand the difference between stretch and compress of a spring. Not that it makes a whole lot of difference for our purposes, but I want you to be able to visualize what's going on. Okay, so we're going to learn how to calculate the potential energy that a spring has when it's stretched or compressed. Okay. So we've talked about one type of potential energy so far. What was it called? One type of potential energy. Starts with a G?
Gravity.
Yeah, we talked about gravitational potential energy was mgh, right? It has gravity right in the equation. So our potential energy equation of a spring is this equation right here. PE equals 1/2 kx squared. You don't necessarily have to have this part up here in your notes. I'm just kind of talking about the other things we're going to talk about with potential energy. So potential energy is equal to 1/2 kx squared. We haven't seen a K before, have we?
Or an X.
Or an X, okay. So what we're going to look at here is K is what we call the spring constant. All right, K is a spring constant, and each individual spring has its own spring constant. Okay, and what the spring constant essentially tells us is how stiff a spring is, how easily it can be stretched or compressed.
Are these in watts?
The spring constant's units are Newton divided by meters, okay, or Newton per meter. That's the spring constant unit. Potential energy, though, its unit is still a joule. Joules. Okay, potential energy is still in joules. Potential energy, kinetic energy, and work are all in joules. Okay, so K is the spring constant. It tells us basically how difficult it is to stretch or compress the spring. And then X, what do you think X might?
Look how far it goes.
Yeah, good. Okay, so X is going to be our displacement, or the distance that the spring has been stretched or compressed. Okay, based on that equilibrium or the static position, how far we stretched it or how far we compressed it is going to be our X distance. And it needs to be in what units? Needs to be in meters. Okay, so a lot of the time you won't stretch or compress a spring very far, so they might give it to you in centimeters. We have to be careful and go ahead and convert it to meters. Okay. Before we start some spring energy problems, we're going to talk about the total energy of a system, or otherwise called the mechanical energy. Okay, the entire energy of the system is made up of the sum of the kinetic energy plus the potential energy. Okay, so the entire energy of the system is made up of kinetic plus potential energy. Remember we talked about kind of that roller coaster as it starts to slide down the ramp. It's going to start transforming kinetic energy into potential or potential energy into kinetic. It'll be a combination of the two. Do you guys remember that discussion we had? That the potential and kinetic energy is on kind of a sliding scale. As we lose potential energy, we gain kinetic. Yes, we remember that, or no, we don't? Yeah, the roller coaster one. Okay, as we slide toward the kinetic energy, we start losing potential.
And what is this in?
Energy's in joules. Energy's in joules, okay? So we can combine energies in the form of one equation if we talk about the conservation of energy. And when I say conservation of energy, I mean that energy before is equal to energy after, okay? And I'm not sure why I labeled the 2's on the left side. I want you guys to think about basically the left side of the equation being the before and the right side of the equation being the after, okay? I just mislabeled them as 1 and 2's. But it means the same thing. It really doesn't make a difference in which side you choose to be the before or after, but I like to just be consistent and know that the left side of the equation is the energy before, the right side of the equation is the energy afterward. Okay, and when we say before and after, I mean a change has happened. So either it started moving, or there was maybe a gun that fired, or something was dropped. Those kinds of things are the change that I'm talking about.
That should be kinetic energy 1.
Yeah, yeah. So this left side, let's think of this as the initial, and this side over here would be the final. Okay, so you can relabel those if you want. I fixed it on the next slide, but I didn't get it fixed on this slide. Okay, so this right here is our conservation of energy equation. This is the big physics topic and point. Okay, that's one of the biggest ones that we should learn about in this class is overall conservation of energy. Okay, so when we talk about the conservation of energy, we can start looking at them in terms of kinetic and potential energy to break down some specific variables. The energy at one point on this system can be found using this equation, and we can solve velocity, we can solve for the height, whatever of those variables we want to, at any one point on the system using this equation, okay? So this equation right here is only for one point along the system. This is not a before and after type snapshot. So if this was, let's say, initial or energy before, and we know that's equal to energy after, what do you think our big equation will look like? Yeah, we're going to just basically double this equation, okay? Oh, sorry, this is just talking. H is height above the ground, V is the velocity. We know what those variables stand for, right? Okay. So here's our total conservation of mechanical energy at any 2 points. Okay, it looks like a big scary equation. It's really not, I promise, okay? What we're taking is we're saying the overall conservation of energy, energy before equals energy after. Energy itself is kinetic plus potential equals kinetic plus potential, and then we're just breaking those equations down even further, plugging in all of our kinetic and potential energy actual equations. Okay, so 1/2 mv squared plus mgh equals 1/2 mv squared plus mgh. Okay. And these 1 and the 2's, you could replace those with I's and F's if you want to think of it as initial and final. You can leave the subscripts off altogether if you know that the left side of the equation is always initial and the right side is always final. You can change those equations to fit what you think or you see as best. As far as the subscripts are concerned, you can't change the equations. As I drop something, if I'm holding something right up here in the air and I drop it, okay, as I'm holding it, does it have kinetic energy or potential?
Potential.
All potential, right? It's not in motion right now. It has no velocity, which means it has no kinetic energy. As I drop it and it reaches about this level, okay, about halfway to the ground, would it have all potential, all kinetic, or both? Both, yeah, both. As it gets close to the ground, basically the instant before it's going to hit the ground, does it have all kinetic or all potential? All kinetic. Okay, so we want to remember that kind of sliding scale as things are falling, as they're moving up and down through a whatever kind of path we're looking at here, okay? So just before it hits the ground, all of its potential energy has been transformed or converted into kinetic. Okay? Let's go ahead and try one here. A stone's being held at a height of 3 meters. We want to find the stone's speed when it has fallen to 1 meter above the ground. All right, so we've got this stone It's being dropped, and it's now 1 meter above the ground. So let's say the ground's somewhere down here. It's in its path. It's in its free fall. We want to think about our conservation of energy equation. So we know that 1/2 mv squared plus mgh equals 1/2 mv squared plus mgh. Okay, so let's start thinking about these terms. What's this 3 meters tell us right here? Okay, so what variable might it give us? Height initial or height final? Initial. And at its starting position, it's 3 meters. Does it have any kinetic energy? No. So we're just going to put a 0 in for that. Okay. I think it's important that we carry all 4 terms through, even if one of them is a 0. So go ahead and plug in that 0. That way you can kind of make yourself accountable for looking at all 4 of those terms. Are we given a mass here? No, we're not. So we're just going to leave it plugged in as an m for right now. Okay. Our gravity is 9.8, and our height is 3 meters. As it's falling, does it have kinetic energy at the ground, or at 1 meter above the ground? It does have kinetic energy, and we want to find speed, so that's what we're going to be solving for, is v there. So we're going to just take 1/2 m, we're going to leave that m in there for right now, times v squared. And then at this point right here, does it still have some potential energy? Yeah, it still has the ability to fall farther. It's not at the instant before it hits the ground. It's still got some potential. So we're going to go ahead and plug in m times 9.8 times the 1 meter above the ground. Okay, I'm going to get rid of these labels here.
This seems difficult to do on your own.
It's really not. We'll work through them. Okay, 9.8 times 3 gives us about 29 something. 29.4. And we're just going to leave the m there, and I'm going to show you what happens here in just a second with that. Okay, 29.4 m is equal to 1/2 mv squared plus 9.8 m. Okay, what terms can I combine here? 9.8 and 29.4. So I'm going to subtract out the 9.8. Subtract out the 9.8 m. Okay, and that gives me 19.6 m equals 1/2 mv squared. So what can I do now with the m? It's going to cancel, right? If I want to get m to the other side, I divide by m, and if I divide by m on the other side, that gives me a 1. So when they don't give you a mass, that means the mass cancels out. So you don't even have to plug in that m, but I wanted to show you that if we carry it all the way through, it does cancel out. Okay? So now we'll take the 19.6 divided by 0.5, and we'll take the square root of that answer. All right, Grace, what'd you get?
6.3 meters per second.
3.13. I got 6.
What about this object since it's moving in the downward direction? What does that tell us about our velocity? It's got to be negative 6.3.
Negative.
Just because it's going downward. The math won't tell you that because you took the square root. But as long as it's going down, it'll be negative. All right, let's try this one. Assuming the height of the top hill of a roller coaster is 40 meters, the car starts from rest. Calculate the speed of the car at the bottom of the hill. Has no more potential to fall any farther. All right, so let's just go ahead and start using our conservation of energy equation. 1/2 mv squared plus mgh equals 1/2 mv squared plus mgh. Okay, so at the top of its path, right up here at the top, if it starts from rest, its kinetic energy must be 0. Very good. Okay, so it only has potential energy. And we saw in the last problem that if there's not a mass given, that means the mass is going to cancel out. So would you rather me carry the m through or just leave it?
Nope. Get rid of it.
Okay, we're just going to leave it out then. So we'll take 9.8 times the original height, which is 40 meters. Okay, and at the bottom, does it have kinetic energy?
Yeah, no.
At the bottom, does it have kinetic energy? Is it moving? Yeah. So we're going to take 1/2. We're going to leave our m out because we know that it's going to cancel out, and we'll solve for v. Does it have any potential energy at the bottom of its?
No.
It does not. And even if you maybe thought it did, what height would you plug in here? 0. So it would still come out as a 0, so we'll just go ahead and plug in a 0 there for potential energy. That's what I mean when I say carry through all 4 terms, 1, 2, 3, and 4, just so you can kind of check yourself that you've taken into consideration all 4 of those things. Okay? So 9.8 times 40 is about 392. And that's going to equal 1/2 times v squared. So we'll divide by 0.5 and then take the square root of that answer. Okay. Nope. Because it's not in free fall, so if we're thinking basically in just terms of velocity, it's moving to the right, which is a positive direction. Okay. If it was free falling, then yeah, we'd be talking in negative. But here, since it's basically moving along a track in the positive direction, we're just going to keep it positive.
Yes.
We're going to take that same type of problem and we're going to twist the question just a little bit. So we saw that once the roller coaster reaches all the way to the bottom of the hill, it has a speed of 28 meters per second. What I want to know now is what height, okay, at what point along that track is it going to have half of that speed? Okay, at what point on that path from the top to the bottom will it have half of its velocity? So will it have a velocity of 14 meters per second? We're going to try and find where that would be. Anyone have any guesses? 20 meters. We think it's going to be halfway exactly.
Is there an equation?
We're going to use the exact same equation we use for conservation.
You're just gonna plug in 14 for your velocity.
Exactly. We're going to plug in 14 for our velocity. We're going to try and solve for our final height here. 1/2 mv squared plus mgh equals 1/2 mv squared plus mgh. Okay, so we still have no initial kinetic energy because it's still starting from rest. So that term's still going to be 0. Our height doesn't change at the beginning, so we're still going to take 9.8 times 40, right? We're going to leave out our mass still like we did last time. Here, since we're halfway down the hill, or approximately halfway, we're somewhere, in between the top and the bottom, are we going to have both potential and kinetic?
Yeah.
Yeah, since we're not at the top and we're not at the bottom, we're going to have a mix of the two. So we'll take 1/2, we'll leave our m out, and we'll have 14 as our velocity because that was basically what the problem stipulated, when we had 14 meters per second of speed. And we're going to take,
Where'd you go?
because the question asked at what height will it have half of the speed, so we're going to take just half of our original speed. It's just basically pinpointing a velocity. We're trying to find where along the track it has that speed. Okay? And we're not going to drop our potential energy because we're not all the way to the top or all the way to the bottom on our track, so we're going to have a combination of the two. So we're going to solve here for that height. We haven't confirmed that it's going to be exactly halfway down the track. It might be, right when it starts. It might be near the bottom. We're going to solve for that height.
What'd you get? Oh.
You got 39.83. Is that right?
I did not.
You got what?
39.
You're gonna have
You need to subtract over the 98, and then you can divide by the 9.8. Okay? So I got my final height to be 30 meters. Right?
Gotcha.
So that means along the track, my car is going to be about right here. It's not going to be at the halfway point. It's going to be before that. Okay, it's not going to be at the halfway point exactly. It's going to be up a little bit higher. Okay, so 30 meters above the ground, basically, or 10 meters below where we started.
I need to get this picture. Example. Is that 0.1?
It's 0.1 kilograms. All right, this conservation of energy is going to be solved the exact same way, except we're not using gravitational potential energy. We're using spring potential energy. Okay, so our equation will look something like this. Oops. Oh, okay. All right.
3.
Our equation will look something like this. 1/2 mv squared, that's still our kinetic, plus 1/2 kx squared, which is our what?
Potential.
Potential of a spring, good.
What? I don't have this.
I didn't give you this full equation. All we're doing is subtracting this right here. This 1/2 kx squared is the equation for potential energy of a spring. So all I did was substitute this in for this equation because it's a spring problem. We've got a coil in there. Okay.
0.06 is the x, right?
All right, so let's just work through it. All right, so listen up. Before this thing is being fired, this coil or this spring has been compressed a certain distance. Okay, so before the thing is fired, at point 1, basically, or before, we've got only potential energy. After it's been fired, or final, it's got only kinetic energy, because after it's released, the spring goes back to equilibrium, and the dart now has all of that energy going with it, moving in some velocity. Does that make sense? Before it's coiled, so the spring and the dart only have potential energy. After it's been fired, it's got all kinetic. Okay? So before, we've got no kinetic energy, plus 1/2 k.
250.
Yep. And then our x is 0.06. We want to square just the x. And that's going to be equal to 1/2 times 0.1 times v squared. And our potential energy final is just 0. Okay, so this thing has been compressed. It's got all potential. After it's fired, it's got all kinetic. Okay, so we've got no initial kinetic energy and no final potential energy. The spring has no potential left to it after it's been fired.
$30.